Hello and welcome to my YouTube channel Petro Intelligence. My name is Shahid Khan and I am a chemical engineer. Today we will discuss how instruments work. In this age of advanced computer control, problems are still caused by the field instruments. The field instruments we discuss in this video are level indicators, pressure indicators, flow indicators, temperature indicators. This video is particularly important when we consider that the data displayed in the control room are for operator control of the process. Data for engineering purposes should be obtained locally at the instrument itself. Further, a large percent of control problems are actually process malfunction problems. Level indication. What is the difference between a gauge glass and a level glass? Simple. There is no such thing as a level glass. The liquid level shown in a gauge glass does not correspond to the level in a process vessel. This picture is a good example. This is the bottom of an amine fuel gas absorber. This tower is used to remove hydrogen sulfide from the fuel gas. At the bottom of the tower, there are three phases. Fuel gas, 0.01 specific gravity. Hydrocarbon liquid, 0.60 specific gravity. Rich amine, 0.98 specific gravity. Because of the location of the level taps of the gauge glass, only the amine is in the glass. The gauge glass simply measures the pressure difference between 2 points of the tower points A and B in picture. That is, the gauge glass functions as a manometer, which measures the pressure difference in terms of the specific gravity of the liquid in the gauge glass. Should the specific gravity of the liquid in the glass be the same as that of the liquid in the tower, both the gauge glass level and the tower level would be the same. But this is never so. The specific gravity of the liquid in the gauge glass is always greater than the specific gravity of the liquid in the tower. Hence, the apparent liquid level in the gauge glass is always somewhat lower than the actual liquid level in the tower. This discrepancy between the apparent level in the gauge glass and the actual level shown in picture in the tower also occurs in any other type of level measuring device. This includes external float chambers, kidneys displacement chambers, and level trolls. The one exception to this is level measuring devices using radiation techniques. The three causes of the discrepancy between the external level and the internal level are foam formation inside tower, ambient heat loss from the external gauge glass or level troll, the liquid specific gravity in the glass being greater than the specific gravity in the tower as shown in picture. Level discrepancies. Let's assume that the gauge glass shown in picture holds 6 feet of amine. Since the bottom tap is in the amine phase and the top tap is in the gas phase, the liquid hydrocarbon is excluded from the gauge glass. To balance out the weight of the 6 feet of amine, the tower would have to have about 2 feet of amine and 6 feet 8 inch of liquid hydrocarbon. That is, the tower liquid level would be about 8 feet 8 inch or 2 feet 8 inch higher than the gauge glass level. If you conclude that we could use the gauge glass level to actually calculate the level inside the tower, you are quite wrong. To perform the preceding calculation, one would have to assume the ratio of the phases. But this is an assumption equivalent to assuming the answer. How, then, does one determine the actual liquid level in the tower on the basis of the apparent liquid level in the gauge glass? The answer is that there is no answer. It cannot be done. And this statement applies to all other sorts of level measuring instruments, with the exception of radiation devices. Effects of temperature on level. The gauge glass will normally be somewhat colder than the process vessel as a result of ambient heat losses. An exception to this would be a refrigerated process. For every 100 degrees Fahrenheit decrease in the gauge glass temperature or level troll temperature, the specific gravity of the liquid in the glass increases by 5%. This rule of thumb is typical for hydrocarbons only. Aqueous or water-based fluids are totally different. For example, suppose the height of hydrocarbon liquid in a gauge glass is 4 feet between the level taps. The glass temperature is 60 degrees Fahrenheit, the tower temperature is 560 degrees Fahrenheit. How much higher is the height of liquid in the tower than in the glass? Answer is 1 foot. Explanation: 500 degrees Fahrenheit times 5 divided by 100 times 1 divided by 100 degree F equals 25 divided by 100. This means that the liquid in the gauge glass is 25% denser than the liquid in the tower bottom. Assuming a linear relationship between density and volume, the level of liquid in the tower above the bottom tap of the gauge glass must be 1 plus 25 divided by 100 times 4 feet equals 5 feet. In other words, the liquid in the tower is 1 foot above the level shown in the glass. Plugged taps. How do plugged level sensing taps affect the apparent liquid level in a vessel? Let's assume that the vapor in the vessel could be fully condensed at the temperature in the gauge glass. If the bottom tap is closed, the level will go up because the condensing vapors cannot drain out of the glass. If the top tap is closed, the level will go up because the condensing vapors create an area of low pressure, which draws the liquid up the glass through the bottom tap. Thus, if either the top or bottom taps plug, the result is a false high-level indication. High liquid level. In our calculation, we had 4 feet of liquid in the glass and 5 feet of liquid in the tower. But what happens if the distance between the two taps is 4 feet 6 inch? You can see picture of the observed result. Liquid circulates through the glass, pouring through the top tap, and draining through the bottom tap. The apparent liquid level would then be somewhere between 4 feet 0 inch and 4 feet 6 inch, let's say 4 feet 2 inch. The indicated liquid level on the control room chart would then be 92%, that is, 4 feet 2 inch divided by 4 feet 6 inch. As the liquid level in the tower increases from 5 feet to 1,000 feet, the indicated liquid level would remain at 92%. Once the actual liquid level inside the tower bottom rises above the top level tap, no further increase in level can be observed in the gauge glass. We say the level indication is tapped out. The same sort of problem arises in a level troll, which measures and transmits a process vessel liquid level to the control center. As shown in picture, the level troll operates by means of 2 pressure transducers, devices for converting a pressure signal into a small electric current. The difference between the 2 pressure transducers shown in picture is called the milliampere output. This milliamp output is proportional to the pressure difference between the bottom and top taps in the level troll. To convert the milliamp output signal from the level troll into a level indication, the instrument technician must assume a specific gravity. Percent level milliamp signal divided by specific gravity. But which specific gravity should the instrument technician select? The specific gravity of the liquid in the level troll, or the lower specific gravity of the liquid in the hotter process vessel? The technician should use the specific gravity in the process vessel and ignore the specific gravity of the liquid in the level troll. This can be especially confusing if the operator then compares the apparently low liquid level in the gauge glass to the indicated higher liquid level on the control panel. Foam affects levels. Trying to predict a vessel level based on the output from the pressure transducers would work only if one knew the actual specific gravity of the fluid in the bottom of a distillation tower. But anyone who has ever poured out a glass of beer realizes that this is not possible. For one thing, the ratio of white froth to yellow beer is never known in advance. Also, the density of the froth itself is unknown and is quite variable. This picture shows a distillation tower served by a circulating thermosiphon reboiler. To some unknown extent, some foam will always be found in the bottom of such vessels. Not sometimes, but always. Why? The purpose of a tray is to mix vapor and liquid. This produces aerated liquid or foam. The purpose of a reboiler is to produce vapor. In a circulating reboiler, the reboiler effluent flows up the riser as a froth. Of course, the flow from the bottom of the tower is going to be a clear liquid. Foam cannot be pumped. But there will always be some ratio of foam to clear liquid in the bottom of the tower, and we have no method of determining this ratio or even the density of the foam. Well, if we do not know the average specific gravity of the foamy liquid in the bottom of a tower, how can we find the level of foam in the tower? The unfortunate answer is that, short of using radiation techniques, we cannot. Split liquid levels. The two gauge glasses shown in this picture both show a liquid level. Many of you may have observed this on a process vessel. We certainly cannot have layers of liquid vapor in the vessel. Rather, these split liquid levels are a positive indication of foam or froth in the bottom of the tower. If the foam is spanning both taps on a gauge glass, then the height of the liquid in the glass is a measure of the specific gravity or density of the foam in terms of the specific gravity of the liquid in the glass. If the foam is above the top tap of both the gauge glasses in this picture, then there will be a level in both glasses. The upper gauge glass will show a lower level because the light foam in the tower floats on the top of the heavier foam. Note that these split liquid levels, so often seen in a process vessel, tell us nothing about the real liquid level in the vessel. They are a sign of foam. This picture is a plot of the liquid level in a crude pre-flash drum versus time. We were steadily withdrawing 10% more flashed crude from the bottom's pump than the inlet crude feed rate. The rate of decline of the liquid level noted in the control center was only about 25% of our calculated rate. Suddenly, when the apparent level in the control room had reached 40%, the level indication started to decline much more rapidly. Why? This extreme non-linear response of a level to a step change in a flow rate is quite common. Before the sudden decline in the indicated liquid level, foam had filled the drum above the top level tap. The initial slow decline in the apparent level was due to a dense foam dropping between the level taps being replaced by a lighter foam. Only when the foam level actually dropped below the top tap of the drum did the indicated liquid level begin to decline at a rate representing the actual decline in the level. Thus, we can see that this common, nonlinear response is not due to instrument malfunctions, but is a sure sign of foam or froth. Radiation level detection. The only way around the sort of problems discussed before is to use neutrons or X-rays to measure the density in a vessel. In a modern petroleum refinery, perhaps 5% of levels are monitored with radiation. It is both safe and effective. The neutron backscatter technique is best performed with hydrogen-containing products. Both the source of the slow neutrons and the receiver are located in the same box. The slow neutrons bounce off protons, hydrogen ions, and are reflected back. The rate at which these neutrons are reflected back is measured and corresponds to the hydrocarbon density in the vessel. This measurement is not affected by steel components inside or outside the vessel. X-ray level detection works with a source of radiation and a receiver, located on either side of the vessel. As the percent absorption of the radiation increases, the receiver sees fewer X-rays and a higher density is implied. The X-rays are absorbed by steel components, such as ladders and manways, which can sometimes be confusing. Either method discriminates nicely between clear liquid, foam, or vapor. Such a level controller can be calibrated to hold a foam level or a liquid level. Of course, this sort of level detection is far more expensive than conventional techniques. Pressure. Pressure indicators. The chief engineer of a process plant had decided to replace the main condenser. Colder weather always coincided with a vastly improved vacuum in their vacuum tower. It seemed as if colder air to the condenser really helped. So, the chief engineer concluded that a bigger condenser would also help during warm weather. It's wrong. The chief engineer failed to realize that the vacuum pressure indicator was not equipped with a barometric pressure compensator. An ordinary vacuum pressure indicator or pressure gauge reads the pressure difference between the vacuum system and atmospheric pressure. When ambient temperatures drop, the barometer rises, or ambient pressure goes up. An ordinary vacuum pressure gauge or indicator would then read an improved vacuum. But in reality, the vacuum has not changed. The opposite problem would occur in Denver, the mile-high city. At sea level, full vacuum is 30 inches of mercury. But in Denver, full vacuum is about 26 inches of mercury. An ordinary vacuum pressure gauge reads 0 inches of mercury in Denver and in New Orleans, because although these cities are at different altitudes, the vacuum pressure gauge compares system pressure only with ambient pressure. But a vacuum pressure gauge reading 25 inches Hg in New Orleans would correspond to a pore vacuum of 5 inches Hg absolute pressure, 30 inches Hg minus 25 inches Hg. A vacuum pressure gauge reading 25 inches Hg in Denver would correspond to an excellent vacuum of 1 inch Hg absolute pressure, 26 inches Hg minus 25 inches Hg. All these complications can be avoided when making field measurements by using the vacuum manometer shown in picture. The difference between the two mercury levels is the correct inches of mercury absolute pressure, or millimeters of mercury, mmHg. A drop of water on the evacuated end of the manometer will result in a falsely low vacuum reading. Pressure transducers. Disassemble a pressure transducer, and you will see a small plastic diaphragm. A change in pressure distorts this diaphragm and generates a small electrical signal. The signal must be quite tiny, because placing your hand on the transducer can alter its reading. A modern digital pressure gauge uses a pressure transducer. This type of gauge, if zeroed at sea level in New Orleans, will read 4 inches of Hg vacuum in Denver. Most pressure signals transmitted from the field into the control center are generated from pressure transducers. Differential pressure indicators simply take the differential readings from two transducers and generate a milliamp output signal. Pressure point location. Locating a pressure tap in an area of high velocity is likely to produce a lower pressure indication than the real flowing pressure. Using a purge gas to keep a pressure tap from plugging often can cause a high pressure reading if too much purge gas or steam is used. A pressure tap located below a liquid level will read too high. Pressure should be measured in the vapor phase. A pressure tap opposite an inlet nozzle with a high velocity will read higher than the real pressure. Flow. Flow indication. The standard method of measuring flows in a process plant is by use of the orifice plate and orifice flanges, shown in this picture. Actually, we rarely measure flows directly. More commonly, we measure the pressure drop across an orifice plate. This pressure drop is due to the increase in kinetic energy of a fluid as it accelerates through the small hole in the orifice plate. The energy to provide the increased velocity comes from the pressure of the flowing fluid in accordance with this equation. Delta P equals kdF over 62.3 times V square. Where delta P equals measured pressure drop through the orifice plate, in inches of water, multiply the measured pressure drop inside by 27.7 to obtain the inches of water. Delta P, V equals velocity of the fluid through the orifice plate in feet per second. dF equals density of the fluid, whether vapor or liquid, pounds per cubic feet. K equals an orifice coefficient. You should look up the orifice coefficient K in your Cameron or Crane handbook, but it is typically a number like 0.6 to 0.8. Checking flows in the field. The competent engineer does not assume a flow indication shown on the control panel is correct, but proceeds as follows. 1. Referring to this picture, place an easy-to-read pressure gauge in the position shown. You can use a digital gauge. 2. By opening both valves A and B, with C closed, you will now be reading the upstream pressure. 3. By opening valve C, with A and B closed, you will read the pressure downstream of the orifice plate. 4. The difference between the two readings is delta P in the preceding equation. Now solve for V. 5. Look at the tab sticking out of the orifice flanges. Look at picture. If the orifice plate is installed in the correct direction, there will be a number stamped onto the tab, toward the flow. This is the orifice plate hole diameter. For example, if you see 0.374 foot stamped on the tab, as shown in picture, the orifice hole diameter should be 0.374 inch. 6. Using the hole diameter, calculate the volume of fluid. Suppose the flowing fluid is water. Assume the area of the orifice is 0.1 square feet. The observed delta P equals 4 psi. Converting psi to inches of water. 1 psi equals 27.7 inches H2O. Therefore, the observed delta P expressed as inches H2O is 4 times 27.7 is equal to 110.8 inches H2O. The linear flow rate, V, in feet per second is found from delta P inches H2O equals orifice coefficient times V square. Suppose the orifice coefficient is 0.6, which would be typical, then 110.8 is equal to 0.6 times V square, proceeds to V square equals 110.8 divided by 0.6, proceeds to V square equals 184.66, proceeds to V equals under root 184.66, gives V equals 13.6. We find the volumetric flow rate, F, in cubic feet per second after multiplying by the cross-sectional area of the orifice opening. Thus in this case, F equals 13.6 feet per second times 0.1 square feet equals 1.36 cubic feet per second. You may notice when you measure delta P that it is a small value, difficult to measure accurately. This means that the orifice plate hole is oversized, and that the accuracy of the recorded flow on the control panel is also poor, or the measured delta P is quite high. This means that a lot of pressure is being wasted, and the orifice plate hole is undersized and restricting flow. Furthermore, the recorded flow on the control panel may be off scale. The reason the orifice flanges are kept close to the orifice plate is that when the liquid velocity decreases downstream of the orifice plate, the pressure of the liquid goes partly back up. This picture illustrates this point. It is called pressure recovery. Whenever the velocity of a flowing fluid vapor or liquid decreases, its pressure goes partly back up. An extreme example of this is water hammer. The reason the pressure at the end of the pipe in picture is lower than at the inlet to the pipe is due to frictional losses. The orifice coefficient K takes into account both frictional pressure losses and conversion of pressure to velocity. The frictional losses represent an irreversible process. The conversion of pressure to velocity represent a reversible process. Other flow measuring methods. A better way of measuring flows than the ordinary orifice plate method is by inducing vortex shedding across a tube in the flowing liquid and then measuring the velocity of the vortices. This is a nice method, as there are no orifice taps to plug. Then there are Doppler meters, which measure the velocity of a fluid based on how the speed of sound is affected by the flow in a pipe. More commonly, we have rotometers, which measure how far a ball or float is lifted in a vertical tube by the velocity of the liquid. But regardless of their relative merits, perhaps simply for historical reasons, the vast majority of flows in most process plants are measured with the orifice plate flowmeter as shown in this picture. Glycol-filled instrument lines. Many of us have seen the following tag attached to level sensing lines or to a flow transmitter: "Do not drain, glycol-filled." This means the instrument mechanic has filled the lines with glycol, mainly for winter freeze protection. Many process streams contain water, which can settle out at low points and, in effect, plug the impulse lines to flow or level sensing delta P transmitters when water freezes. Note that there is not a lot of difference between measuring a flow and a level. They both are typically measured by using a differential pressure signal. Naturally, just like level indicators, the flow orifice taps can plug. If the upstream tap plugs, the flow will read low or zero. It is best to blow the tap back with glycol, but that is not always practical. If you blow the taps out with the pressure of the process stream, you do not need to refill the impulse lines with glycol to get a correct flow reading. But the lines have to be totally refilled with the same fluid. If you are measuring the flow of a single-phase liquid, just open valves A, B, and C shown in picture for a few minutes. If you are working with vapor at its dew point or wet gas, there is a problem. If the flow transmitter is located below the orifice flanges, you will have to wait until the impulse lines refill with liquid. Open valve B and close valves A and C. Now wait until the flowmeter indication stops changing. It ought to go back to 0 if the lines are refilled. Zeroing out a flowmeter. The indicated flow of acetic acid is 9,000 liters per day. The instrument technician checks the flowmeter to see if it is drifted by opening valve B with A and C closed shown in picture. It should go back to 0, but a reading of 2,000 liters per day is noted. The full range on the flowmeter is 10,000 liters per day. What is the real flow rate of the acetic acid? The answer is not 7,000 liters. Why? Because flow varies with the square root of the orifice plate pressure drop. To calculate the correct acetic acid flow, 9,000 square minus 2,000 square equals 77 million. 77 million, carat 1 divided by 2 equals 8,780 liters per day. The lesson is that near the top end of its range, the indicated flow is likely to be accurate, even if the meter is not well zeroed or the measured delta P is not too accurate. On the other hand, flow meters using orifice plates cannot be very accurate at the low end of their range, regardless of how carefully we have zeroed them. Digitally displayed flows also follow this rule. Temperature. Temperature indication. This picture shows an ordinary thermowell and thermocouple assembly. The thermocouple junction consists of two wires of different metals. When this junction of the wires is heated, a small electric current, proportional to the junction temperature, is produced. Different metal wires make up the three most common junctions, J, H, and K. It is not uncommon for a thermocouple, regardless of the type of junction, to generate too low a temperature signal. If the exterior of the thermowell becomes fouled, the indicated temperature, generated by the thermocouple, will drop. The problem is that the external cap of the thermowell assembly radiates a small amount of heat to the atmosphere. Normally, this has a negligible effect on the indicated temperature. However, when the process temperature is 600 to 800 degrees Fahrenheit, the thermowell is in a vapor phase, and the thermowell becomes coated with coke. I have seen the indicated temperature drop by 40 degrees Fahrenheit below its true value. To verify that fouling of a thermowell is a problem, place a piece of loose insulation over the exterior thermowell assembly. If the indicated temperature rises by 5 or 10 degrees Fahrenheit, then fouling on the outside of the thermowell is proved. Short thermowells. For a thermocouple to read correctly, it should be fully inserted in a thermowell, and the thermowell itself should extend several inches into the process liquid. If the process stream is a vapor, which has poorer heat transfer properties than do liquids, the thermowell, especially if the external insulation is poor, should extend more than 6 inches into the process flow. To check the length of the thermowell, unscrew the thermocouple assembly and pull it out, then simply measure the length of the thermocouple. This is also a good opportunity to verify the control room reading with a portable temperature probe or a glass thermometer inserted in the thermowell. About 5% of the TI points used are not located where the unit piping and instrumentation diagrams, PNIDs, show them to be. Then, pulling the thermocouple from a point in the process sometimes causes an unexpected drop to ambient temperature at an entirely unexpected TI location. Safety note. This picture is somewhat misleading. It implies that most thermowells are welded in place. Typically, thermowells are screwed into a 1-inch nozzle in the vessel wall. I talked in the preceding section about unscrewing a thermocouple. This is perfectly safe. The same comment applies to extracting a screwed-in dial thermometer from a thermowell. However, sometimes less experienced people have made a deadly error in unscrewing a thermowell instead of a thermocouple. Unscrewing a thermowell opens up the process fluid directly to the atmosphere. Ram's horn level indication. A too short thermowell in the side of a vessel will increase in temperature when the liquid level rises to submerge the thermowell. This picture illustrates a common method of exploiting this phenomenon. This is the ram's horn interface level indicator. The thermowell extends to the vessel wall only and is poorly insulated. The curved pipe below the thermowell permits liquid to drain out of and through the pipe enclosing the thermowell. Usually, 3 or 4 such ram's horns are vertically set 18 inches apart. A sudden temperature increase at a ram's horn is a foolproof method of detecting a rise in a liquid level. Especially in fouling or plugging service, I have seen this simple, archaic method of level indication succeed when all else fails. If 2 temperature readings from the same point in the process disagree, the chances are that a temperature indication is more accurate than a temperature control signal. The temperature signal used for control has usually been converted from its direct milliamp output to operate a control station. The temperature indication is generated right from the junction of the thermocouple, and hence there is less chance for error. That's all, gentlemen. If you like my video, please follow my YouTube channel Petro Intelligence for more videos. Good day and good luck.